I am super grateful to be here. Just from the people I've met already, that we have so many passionate and really great people. I can tell that Redwood Energy, their team is really just a lot of good people attracting good people, right? I met Jasmine here on the plane, and before Sean takes 2 trips to drive me and my family back to the Airbnb, we're waiting at the airport, and Jasmine gets the entire terminal to sing my 4-year-old happy birthday. Who does that? So, thank you, Jasmine. Yeah, so this project, this is about grid interactive load flexibility control of multifamily heat pump water heater systems. So what does that mean? So our goal is to work with the utilities to design a control these heat pump water heating systems to be able to use energy when they want us to. Right, we've seen the duck curve. We've seen how these utilities, they can make a lot of clean energy at certain times, but at other times it's a lot more difficult. So what we're trying to do is we're trying to use that energy at the right time, and we're trying to use it that's going to be a benefit for the utility and for the consumers, right? So I really swim in the details of heat pump water heating systems. So I want to ask all of you, who's involved in domestic hot water in general? Great, so there's a lot of you. Perfect. And I've heard a lot of talk about water heaters, of course. Is there anyone very interested in commercial heat pump water heaters? Or do you have experience? Nice. There's a lot of us. That's great. So I'll try not to dive too deeply into the details about heat pump water heaters themselves, because this is about how they're going to interact with the entire system and serve the utilities. But we do need to have a basic understanding of how they work to understand the really great data that Greg's going to come up with later. So next slide, please. So our team on the project that I'm going to present today is Redwood Energy is priming the project. And so they're the ones that have the fun job of trying to rally all the contractors at the buildings and keep our team focused to be able to hit the deadlines we need to for the funders. And then ZYD Energy, led by Jan de Zong and his team of really cool engineers, they've actually created this controller based off the research they've seen and the needs they're seeing both in residential and commercial buildings. So they've designed this controller that I'll show you, and they're the ones that are leading the drive to implement this controller. And then Ecotope, we're a design and research engineering consulting firm. So we really like to partner with manufacturers to make sure that they understand the conditions that they'll be seeing in these buildings, and so that they can handle the conditions and work most efficiently that way. But we're also a design firm for both market rate and low-income multifamily buildings. So we can put these systems in the buildings, monitor them, and then figure out how we can optimize on the system level and work with the manufacturers to figure out how they can optimize on the heat pump level. So it seems like a really great partnership, and it's been a lot of fun partnering with ZYD and Redwood Energy and Artemisia Energy. Did I pronounce that right? I've only ever called him Greg. So Greg Pfotenhauer he's gotten a lot of great plots out and a lot of great explanations on how these systems are actually operating. And then Gabe Kraus and Lonnie Grafman were involved in the M&V design up front in the buildings that I'm going to talk about. And so they were instrumental in making sure that we have solid data to understand how the systems are doing before we retrofit this controller in. So next slide. And so a little background on the project. You can go to the next slide, please. I think I've explained most of this, but we're demonstrating a controller that provides heat pump demand response that can communicate with the grid to understand what the forecasted utility pricings will be and understand how clean this energy will be coming out of the grid in the next day or so. And then we're going to use that energy when it's clean and when it's cheap, because we want it, of course, we want it to be lowest carbon as possible, and we want to benefit the customers that are going to install this controller, which will really spread the implementation of the controller if you can actually get cost savings as well as cleaner energy out of it. So, and of course, a big difficulty with installing heat pump water heaters on the commercial scale is it's always been really scary for installers. So they always add what they call the unknown multiplier, or we call the unknown multiplier. And so they're adding an extra $10,000 because it's a heat pump water heating system if we're talking about a small system. So luckily there's a lot of good contractors that are getting up to speed on these heat pump water heating systems. I think you'll hear from one later today. But we still need to make sure they're seeing this as simply as possible and understanding really easy interfaces between what they know and what they're now tasked with installing. So next slide, please. So Redwood Energy has gotten 3 different buildings to volunteer to install this controller, and they're all very different buildings. So the first building is Monterey Gateway, so it's a 75-unit multifamily building for low-income seniors, and that has one central heat pump water heating plant that serves the entire building. And then we have Bayview Heights in Eureka that has 12 heat pump water heating plants, each serving like 3 to 6 units. So they have these little integrated heaters and additional tanks, and so we have 12 different heat pump water heating plants. And then we have Santa Rosa Veterans Housing, which is a group of tiny homes. And so we have, I think it says here, 7 tiny homes, each served by a single Sanco 2 heat pump. So those are the residential monoblocks that are very large for one house, but they can serve a lot of dwelling units on their own. What's the next slide, please? And so an overview of this Locust technology, and I'm trying to contextualize this into a larger view because there are multiple ways to apply load shift in these commercial heat pump water heating systems, and ZYD's approach is a really cool way to try to keep it as simple as possible. A lot of complex things happening inside the box, but it's just a box to the installer and the resident. So next slide. So first we'll lay the foundation and talk about what a heat pump water heater is. So as most of you will know, a heat pump is, we're just harvesting heat from the surrounding air or a source, and we're going to put that into something useful. So in a heat pump water heater, the useful media is domestic hot water. So there's a few different ways that they do that, and we're talking mostly on the commercial scale here, just because this project's commercial and I dive into commercial details all the time. So we have two main form factors, but there's 3 components in these systems that are really crucial. The first is the heat pump itself. It's pulling heat from the air, putting it in the water. The second is the storage that's paired with this heat pump, because these heat pumps like really consistent conditions, and they're not very high recovery, so they need this storage to handle those high peak draws if everyone decides to take a shower at the same time. And the third thing in all of these systems is the controls. They need to know when to turn on so that they can keep that storage charged and make sure that they're receiving the conditions they need and not overheating their own water. Right, so the first form factor is, it includes single pass or multi-pass. So I won't dive deep, but essentially the single pass system, we're stratifying the tank. So we have nice cold water on the bottom, hot water on the top, and we're trickling water through the heat pump to be able to heat it all the way up to that high temperature so we can maintain that tank stratification. The multi-pass heat pump, we just have a pump on a single speed, and it's just ripping the water through the tank, and it'll mix that tank up. And then the integrated heat pump is what you might be used to on the residential side, but they make commercial sizes as well. And they have all of the components packed into a single package. So you could go to Home Depot and you could get one unit with the storage, electric resistance, and the heat pump. Now that I say that out loud, I don't know if there's Home Depots down here, but that's my, yeah, okay. Okay, yeah, any big box store. And you can get everything just in a single package. So it's usually pretty inexpensive to install and to purchase, and it's a lot simpler because everything's already integrated together. But what you want to focus on here for how we're applying load shift with the ZYD controller is there are two connections on each of these systems to the building. There's cold water coming in and there's hot water coming out. And there's hot water circulation that's going to be a third connection that'll apply to two of the buildings, but we're going to talk about the simpler building today just so you can digest the data a little bit. So just dedicated hot and cold connections is what you'll want to keep in your mind. And next slide, please. Sorry, I don't have a cool acronym that's going to tie back into that, but yeah, I'm sure Jasmine will have my back here. Just go ahead and yell it out. So the typical operation, we want to understand the controls of these heat pumps a little bit. And what's cool about at the heat pump level, this operation is really simple, right? The sensor gets cold and the heat pump turns on. Sensor gets warm, the heat pump turns off, right? But how that interfaces with the building and how it interfaces with the stratified storage is we'll start with a fully charged storage tank. The building will use hot water. Everyone gets in the shower in the morning, and we have the cold water coming in the tank to make up for the hot water that's going out of the tank. So we have this nice layer of blue on the bottom, which is cold water that just fills the tank from the bottom up. And as soon as that cold water hits the sensor, the heat pump's going to turn on. And now your heat pump is running and your storage is providing water to the building. So that's how you're satisfying the peak load. The heat pump and the storage working together to satisfy this load in the morning. And your tank can drain down almost completely when it's stratified storage. So we're getting a lot of energy out of this tank. We're not mixing the tank up and making it unusable by the time it's down to 115 degrees. Most of the tanks can be down at cold water temperature, 60, 70 degrees depending where you are. So we're getting a lot of BTUs out of this tank with the stratified storage. And then after our load subsides, after everyone's done with breakfast and dishes and have gotten out of the showers, that's when the heat pump can keep up and trickle charge this storage tank back to full. So after that sensor gets hot again, or maybe if our controls are one step fancier, we'll have an off temperature sensor down here. After that sees warm water, the heat pump's going to shut off and it's ready for the next peak. Let's go ahead and next slide, please. So here is that in graphical form, right? So our blue line here is our hot water usage. So we see that morning peak and afternoon peak. This is going to change on a day-to-day basis, but in general, we'll see 2 peaks in a day of hot water usage. Maybe we'll see how Greg's data aligns with that later. The green line here is the storage. So if you're thinking about the picture on the last slide, that green line, the volume of storage is how much of that red hot water is available in the tank. And so we start with a fully charged tank at the beginning of the day. Oh, and the red line is the heat pump turning on and off. Right, so you can see the heat pump is on for a long time in the day because it's just slowly trying to keep up with keeping this storage charged while the storage is trying to handle these peak loads. So how that looks throughout the day is the storage starts fully charged. We have our morning peak. You can see the storage just drops off significantly during that peak, and the heat pump turns on as soon as that storage volume starts to drop. Right, and then that peak subsides, hopefully before we're completely out of storage if we've sized the system right. And then the heat pump will slowly recharge that storage before the next peak period. So then you'll see this smaller peak in the afternoon. This is happening during the time when our electricity is a lot dirtier, right? So you can see it's a slightly smaller peak in some cases, but the heat pump is running during that peak usage period, in that typical 4 to 9 period to satisfy that load. So next slide, please. So if we want to apply load shift and we want to shift the energy usage out of this 4 to 9 period, or whatever period the utility deems most dirty for that region, we just want to turn the heat pump off during that period, right? Because that's the main energy usage in this domestic hot water system is the heat pump trying to charge that storage. So in order to do that, we just need to make sure that we have enough storage available to solely handle the peak load with the storage on its own, instead of having help from the heat pump water heater. So you can see in this plot, we'll have a little over 1,500 gallons of storage, and that storage on its own will drop down as this load happens and during what we'll call the shed period, when we don't want energy usage. So next slide, please. So the way ZYD's locus controller handles this, locus is load optimization control using storage. Another great acronym that Jasmine and I can work on. Their approach is to have simple connections to the heat pump system and to the building and to an additional storage tank that they can manage using their intelligent controls. So they'll talk directly to the utility to see how clean the energy is going to be and what price signals they'll see in the next 24 hours. And then they'll talk directly to the cloud to be able to talk to the resident or the building owner if anything goes wrong. But more importantly, they're assessing and then they're drawing from the heat pump itself to charge this additional storage when we don't have dirty electricity. When the price signals are lowest, based on their forecasting, they're going to charge this storage tank up, and then when the price signals are high, they're going to isolate the heat pump, not draw from the heat pump at all, and they're just going to let the storage tank handle that load. So the heat pump is only connected to this locus controller, and the additional storage is only connected to the controller, and that's how the installers are going to be able to install this simply, while the really intelligent locus logic will determine when it will make the most sense to draw from that heat pump and charge the additional storage to handle the load. Next slide, please. So here's a look at the simplest version of the locus controller. So these are the guts inside the controller where we have modulating valves and a circulation pump to be able to charge that additional storage. So when electricity is cheap and we're in the charge mode, it's going to pull hot water from the top of the heat pump, and it's going to charge that storage from the top down so it's nice and stratified. And then it's going to pull cold water from the storage and feed it to the heat pump. So all the heat pump sees right now is a slow and steady draw as the controller is pulling this water out of it. After that storage is charged, we'll put it in idle mode, or ZYD will, and we have a fully hot storage tank ready to be used during that peak load during the shed period, and the heat pump will handle the load on its own. So it'll see the draw just as it would if it didn't have the controller attached. And then finally, during the shed period, we are discharging this storage, and we're isolating the heat pump. So the heat pump doesn't see any draw; it can just sit there happy and asleep, and this extra storage will draw down. And they're going to size this storage to be able to cruise right through that shed period without turning the heat pump on. And next slide, please. And so that's one approach to load shift, which is really accessible for both residential and commercial buildings, and both integrated and split system heat pumps. So in parallel with this project, there are a lot of projects that are moving forward with load shift using a different control strategy, and that's really tuned into split system heat pumps or monoblocks with separate storage and large commercial buildings. So a few different manufacturers have implemented this other load shift strategy where we'll have 3 different sensors in the tank, and the heat pump's going to look at a different sensor depending on what it wants to satisfy. So if you advance, I think there's an animation here. Right? Yeah, pretty fancy, right? Yeah, I worked hard on that one. So if we're oversizing the storage to be able to handle this peak load, we want as much storage as possible before the shed period, before the heat pump turns off. So they're going to look at a sensor on the bottom of the tank and make sure that sensor stays warm. As soon as the shed period starts and we want the heat pump to turn off, you can advance, then we'll allow that storage to draw all the way down and reference a sensor at the very top of the tank before the heat pump will turn on. So you can see about 80% of the tank here is completely cold, 60-degree water, before that heat pump tries to turn on and recharge it. So this is what large commercial manufacturers are doing, but this system could also benefit from Locus's intelligence by understanding when we're going to try to load up that tank and at what periods we're going to try to shed to give the resident the most value and give them the most price savings, which awesomely translates to the cleanest energy usage because the utilities are going to charge the least when there's most solar production. So this is existing right now with multiple manufacturers. Locus could really improve upon the controls of this system, and they have their own flow and intelligence for a wider variety of systems that includes those integrated heat pumps as well. So next slide. Yeah, so now we'll talk about the retrofit of these systems. So I talked about the 3 buildings, but I have time to dive into Santa Rosa one more level. All right, so next slide. So Santa Rosa were these 14 tiny homes and a heat pump system serving 7 tiny homes at a time. So these Sanco 2 systems are extremely efficient. If any of you have worked with them, I haven't seen COPs higher with any other equipment, but I'm sure it's possible, but this is what I've seen. And this building does not have a recirculation loop, so those heat pumps always see nice cold incoming water. So we're just seeing really great COPs before we do anything with the controller in this building. And on the next slide, you'll see the cartoon version of the heat pump system itself. So I've explained this with a single storage tank and a heat pump to charge it, hot and cold building connections, and then advance. And so we're going to tie the Locus into the hot and cold heat pump storage connections. And we're going to put just because this is a new product and it's in the research phase, we're going to be able to isolate it, not completely disconnect the heat pump system from the building and connect directly to the controller, but we're going to put in ball valves in a way that we can simulate a completely dedicated connection, but still open those ball valves back up if the controller stops working for any reason. So advance one more time, please. Then we're going to tie the Locus into the hot and cold connections for the building. So then now we have, with those 2 closed ball valves, we have dedicated connections to the heat pump and we have dedicated connections to the building. In the other 2 buildings, we also have hot water return. So we'll have a dedicated connection to the return line as well. And advance one more time. We'll have a completely separate storage tank for additional storage that only has to connect to the Locus controller. So next slide, please. So here's the real version. This site's been installed and Greg has some great data to share on it. But you can see that the controller is in the middle of the system between, this is the Sanco 2 storage tank, or Gen 3, so it's a stand-in storage tank, and then a controller mounted to the wall. And then we have the connections tying into the existing building connections and an additional tank on the opposite side of the controller that Locus is going to draw from the heat pump system to charge up. And in this picture on the right here, you'll see the controller is nice and compact with insulated piping and everything, and this is what's manipulating those draws and making all those difficult decisions to figure out when we can charge these storage tanks up without overwhelming the heat pump, and when we want to turn that heat pump off and only use additional storage to save the most money on the bills and use the cleanest energy throughout the day. And next slide. With that, actually I should probably ask for a question or two if anyone has any before I send over to Greg. Yeah.
Did you use multi-pass in any of this? You referenced it at the beginning. Are you using any multi-pass systems?
We're not in this project, but it will. Yeah, are we using multipass in any of the systems that we're demonstrating here? We're not, but it can operate the same way. The multipass will just maintain that 140-degree storage temp, and then we'll draw from the multipass system to charge this additional storage in a stratified manner, right? Because the multipass systems, they can't draw down to 80% cold water because as soon as that heat pump turns on, it'll mix it all up and send cold water to the building. But the additional storage is always stratified, so it can send that to the building without disturbing the heat pump. Yeah.
Just curious about the controller, if it can be connected to the BMS, or if it can operate independently with its own logic, and how, do you need to have a BMS contractor in to program it, or does it come self-packaged with an internet connection to be able to do what it needs to do?
Yeah, it uses its own logic, and I think they used Wi-Fi on all these controllers, but it doesn't need any sort of building communication. All it needs is the heat pump will have its own completely separate controls that don't interface with the controller, and the controller will just simply draw off this heat pump and make the heat pump think it's just seeing a simple building draw. Right, so all those controls, connection with the utility, it's all internal to the controller, so the building owner doesn't have to think about it. Any other? Yeah.
On residential heat pump water heaters, they typically are hybrid, so they have electric resistance backup. So have you looked into ways of having algorithms that can minimize the use of the electric resistance backup and take that into account as far as when you run the heat pump, when you run the electric resistance backup to optimize the things that you're trying to optimize, which are price and low carbon?
Yeah, so another building that I didn't dive into here was in Eureka. They use those integrated heat pumps, and the locus controller can slowly draw from those heat pumps when there's not a lot of hot water usage. So slowly enough so it doesn't trigger that electric resistance. And then during these peak loads where you'd normally see electric resistance, it can actually kick in that additional storage so the heat pump doesn't have as intensive a draw on it. So they have thought about that. I can't dive deeply into how they actually control it because their intelligence is in there, and I understand it at a surface level, but they can leverage that additional storage so the heat pump doesn't get overwhelmed even in high peak loads. Any other questions? All right, with that, I'll hand it over to Greg. Thank you. Thanks, Greg.
Okay, so thanks for teeing it up. That was great. Hopefully I won't lose you all or put you to sleep. I'm going to start with some baseline data before we kind of dive into the results of this study. Next slide, please. So, all right, sorry for folks in the back who can't see this, but I wanted to kind of show you all three sites, even though we're going to focus on Santa Rosa today, just to kind of contextualize like what's the problem we're actually trying to solve, which is reducing cost, kind of matching the grid, right? But we have all these things called people in our buildings, which are challenging to deal with. They're wildly unpredictable. They like to use hot water at weird times. So we have kind of our like Papa Bear, Mama Bear, Baby Bear kind of situation here, right? Gilroy is a really large site, 75 units, averages about 3,400 gallons per day of hot water demand. And you can see, everybody kind of evens each other's daily usage out. It's a lot tighter. If we go down to the next size system, which is much smaller, 7 units, 83 gallons of storage, we're down to like 100 gallons per day on average, but we have a lot more outlying days, right? We've got some days where we've got 500 gallons or 400 gallons, whatever. Go to Eureka, which is our smallest system, 3 to 6 units per each one of these 12 systems. Our average daily demand is anywhere from tens of gallons up to 200 gallons per day, like this one on the bottom. And we've got all these outlier days. That might be tenfold increase. So point here, people are really unpredictable, and ultimately this is kind of what we're trying to optimize around is somebody wants to take a bath at 2 p.m. or whatever. Next slide, please.
Wait.
Yep.
What is percent RSD?
Oh, I'm sorry. So percent RSD is just sort of a measure of dispersion. It's relative standard deviation as a percent. So all that is the higher that percentage, the sort of more spread out the data is. So one standard deviation for Gilroy is within 15% of the mean. If we go down to like some of these smaller sites over here, our one standard deviation is equal to the mean. So, for instance, for this one standard deviation is, you can see how much further out the mean is compared to the median because we've got all these outlier days. So it's a relative measure of dispersion. The bigger the number, the more dispersed the data is. Does that make sense? Okay. Sorry for not explaining that.
What
Yeah.
do you design for? Like in that top one, what are you designing for along that line?
So that might become more salient if we look at daily or hourly demand patterns. So go to the next slide here. All right, so to start with Gilroy, this looks kind of chaotic, but this is each hour of the day, and each dot or within our box is a hourly flow. So you can see we're kind of peaking twice, like Evan said. But we've still got all these outlier days, but again, still pretty tight. If you go to the next one, this is Santa Rosa, a much smaller system. Any one person's decision to take a bath or shower at 2 p.m. or whatever, there's a lot more chaos in the data. So the optimization problem is a lot more challenging, right? If you go to the next one, Eureka, it's even worse, right? Like there's really a good chunk of our hours are outliers just because we have fewer people, and any one person's decision to, like I said, take a bath at 2 p.m. is going to impact our storage much more, and therefore our ability to kind of predict that is impacted, right? So again, the point here being people are unpredictable, and this gets a little more challenging with smaller systems. Does that kind of help answer the question?
Yeah.
Okay. All right. Next slide, please. So let's look at Santa Rosa a little bit, since that's what we're going to be focusing on. Like Evan said, most people sort of 2-peak daily profile. We've got a morning shower peak, and then an evening, people are doing dishes and whatnot around 6 p.m. At Santa Rosa, we've got 2 systems, right, east and west. They're a little bit different, similar shapes in terms of their usage, but 100 gallons per day, 175 gallons per day. This is a stand-in system, so we have really stable COPs over a long range of temperatures. And overall, we're getting an efficiency in our baseline period around 3.5. Next slide. All right, so let's recontextualize this. What are we actually trying to do? Next slide, please. So all we're trying to do here, again, is just shift when we're actually charging the tank to minimize costs, right? We don't want to be charging the tank at 5 p.m. when the grid is dirty. And we're doing that a couple of different methods. One, we're using sort of these representative price signals from CalFlexHub. These are representative grid price signals based on the time of year, right? So we have kind of a summer peaking profile where we've got really late afternoon peaks from AC loads and that kind of thing. We've got more of a winter profile with kind of a double peak. So we're sort of testing the locus's operation against all these different price signals and trying to optimize costs by shifting to these lower cost periods like in the belly here. Next slide. One other thing we've started doing is in real time optimizing against actual greenhouse gas intensity signals from the grid. So this is kind of chaotic. This is just 7 days. This is a forecast of greenhouse gas emissions intensity, marginal emissions, over a 24-hour period for 7 different days. And you can see how chaotic it is. So while we're trying to match people's, or account for people's usage, we're also trying to optimize against this fluctuating price. So it becomes a really challenging optimization problem. The locus is constantly reading these forecasts and adjusting when it's going to charge based on what it thinks people are going to do and what the price is going to be later in the day, right? So we're constantly trying to minimize based on all this. Next slide, please. For performance evaluation, we had about a year of baseline for each of these sites. I'm going to focus on Santa Rosa. We ran a bunch of tests for the CalFlexHub and also recently started doing some tests against the MIDAS greenhouse gas intensity data. And we've been doing that for about a year. Next slide, please. All right, so Evan touched on a bunch of these, but outside of people, we have a bunch of other things we kind of got to account for. The heating capacity of the compressor relative to storage and demand, right? So how long is that recharge time? That impacts like how much we can squish into a certain period or shift around. Eureka, for instance, is about a 25% of the heating capacity, but with roughly the same amount of demand, right? So it takes much longer at Eureka to do the same amount of work, essentially. Recirculation, if that's present, that's an additional load on the system. We have seasonal variation, right? Colder incoming water temperatures, colder air temperatures, that affects performance. Hot water demand, we talked about that a lot. And then, like I said, our price signal characteristics, which may be changing every 5 minutes if we're talking about greenhouse gas intensity. So lots of things that are impacting our ability to do this. Next slide, please. All right, results. And I think I got 5 minutes left, yeah? Okay. All right. The SANCOs are really nice because we have a really stable COP over a long range of temperatures and conditions. Down at the bottom here, that's pretty much just on the left side, that's kind of just maintenance, maintaining against heat loss from the tank. But things are pretty stable over a long range of temperatures, so that's nice. Next slide, please. All right, so I'm not going to show all the tests we did, but this is an average plot from one of our more summer-like price signals. You see we've got this in black, we've got this late afternoon peak where our price goes up about tenfold. So what we're trying to do is move all of our compressor usage away from that peak. In the dark blue and orange lines, that's east and west. This is kind of just, if we let it go, let the SANCO do its thing, we still got quite a bit of usage during that period. Now with putting the locus in there in that dotted line, we've predicted that we have high demand at the end of the day and a high price. We've moved a lot of that successfully. You can see we dropped down to basically 0 during that period. So the locus is doing this all by itself with that additional storage. And I'll get to quantitative results in a minute. Next slide, please. This is more of a winter price signal where we have 2 peaks, so less time to kind of shift load. Less ability to reduce costs just because we don't have as much time to shift our load. So in this case, we still did a pretty good job. You can see how much we reduced the load, but there are always going to be days where we just, demand is too high. We can't fit all of that compressor usage into the belly of those 2 peaks, and we're going to have days that we fail. So our ability to do this really depends on the complexity of the price signal and people's demand patterns. Next slide, please. For those two tests, this more summer test and the winter test, they were pretty successful. We had a 75% cost reduction on the summer one. The upper threshold is probably 90%, 80 to 90%. So we got most of the way there without impacting people's ability to get hot water, right? Because ultimately we don't want to impact people's hot water delivery. We actually improved hot water delivery. And then in the winter test, we got up to 65% on the west side and 37% reduction in cost on the east side. The difference there is largely a function of demand. The east side is almost twice the demand of the west side, and so the number of days where we just are not going to be able to fully shift all that to the midday is much less. Next slide, please. All right, so I don't know if you can see this real well, but this is every day during the winter test period. The blue line is kind of like a theoretical maximum for lowest cost, and each one of the gray dots is a baseline cost normalized to in dollars per kilowatt hour. Each one of the red dots here is our actual locus optimization. You can see across, from 0 gallons of hot water per day up to almost 200 gallons of hot water demand per day, we were really able to keep that pretty tight. There are always going to be outliers like this one here. Who knows what happened? We can't predict demand perfectly, but you can see how much we've reduced our cost compared to baseline. Next slide, please. How much time do I got? Okay. All right, so I want to walk through some of these scenarios, specific days, because I don't want to lose us in the forest here. So this is one scenario, and to kind of orient you to the plot, in pink we've got the compressor operation. In red, we've got sort of an estimate of demand or of storage throughout the day. So that's how much charge we've got in our tank. Blue, light blue is that price signal, and then green is hot water demand throughout the day. So in this case, we've got, for day one, we've got 136 gallons of hot water demanded. Most of that happened kind of in the middle of the day, and the locus predicted that we're probably going to have a bunch of demand later in the day, and waited just before peak to charge up the tank. We were able to maintain that storage until beyond peak. We still have about 40, 50 gallons of peak at midnight there. And now we're able to recharge again on the second day to get us back up to a full charge. Day number 2 had 279 gallons of hot water demand, so almost double. And even though we had much greater demand, the locus started charging much earlier, and we were able to ride out that peak and just made it to midnight. We ran out of storage, completely avoided what would have otherwise been a really expensive charge during that peak on that second day. All right, next slide. I'm going to skip a couple of these, but like I said, some days we fail. I don't really know what happened here, but like apparently everyone decided to take a bath for about 7 hours. And no matter what we did, I mean, we started charging at 4 in the morning. That compressor was running all day. There was just no winning. So there are always going to be days that we fail. But overall, like I said, we got a 60% reduction during, yeah, this is the summer one. 75% reduction overall. That additional, the days we miss are mostly days like this where it's just excessive demand. Next slide. You can skip a couple of these. Next slide, please. I didn't really touch on Midas, but we're doing the same thing, just with much more variable greenhouse gas intensity signals. So I'll skip that for now since we're out of time. But so what do we learn from this? Next slide, please. We have a lot of challenges. So risk versus reward. Deciding to wait to charge a little bit later with the hope that we can eke out a little bit more cost savings, or being a little more risk averse if we think that people's demand patterns are going to be all over the place. So there's always that trade-off, right? How much are you willing to bet at the casino of people's hot water demand? Baseline performance issues, we talked a little bit about those. I won't go into too much detail, but every system is a little bit different in terms of how able we are to sort of shift load around. And then evaluation, like how do we evaluate this? Every day is different. We can't just kind of match days up. We have to apply some sort of counterfactual to evaluate how well we did, and that's always going to be a challenge. There's no set of standards right now to be able to evaluate this stuff perfectly. Next slide, please. Next steps, we got some more retrofitting to do and a bunch more data collection on Gilroy and Eureka. Santa Rosa is going to keep going. Next slide, please. And ultimately, takeaways here. What do we learn? The Locust did really good in terms of being able to shift demand, reduce cost. This was achieved while improving hot water delivery. It's applicable to any type of system, but further refinement of the system is always going to be necessary to improve our ability to shift load. So, thank you. Questions?
One of the questions on the Locust, like you got these 2 tanks with valves and pumps.
Yep.
My experience in solar thermal, and the more valves and pumps go in, they break over time. Nothing lasts more than 10 years. Why not just go to a bigger tank, like a 200 or 300 gallon tank, because you're stratifying it? Why not just?
So we did in this system. Yeah. So I think the question is why not just add a bigger tank? And Evan can probably explain this better, but it really depends on the system. We did add a secondary tank, right, in the Santa Rosa system. It's load opposition control using storage, so storage being the key there. But we need some sort of controller in the middle, at least for this system. Yeah, do you have a better explanation for that? Or
Yeah, I could add to yours. So I did have one slide with multiple sensors and just one large tank.
Got it.
And so I think Locust's intelligence could be applied to that really well. I think there's fewer applications in terms of integrated heaters and recirc management that make that single tank more difficult. But for split systems in general, especially the commercial scale, I think that's a really good solution to eliminate pumps and valves. But this will spread a wider array of applications.
And if you're retrofitting and you don't have the storage.
Right, yeah. If you don't have storage with 3 or 4 thermal wells, like tank manufacturers don't tend to put those in.
other questions?
Because we have a very busy schedule today, 2 things. Yay!